This question is, consider the function h of x defined as follows. For values of x greater than 0, h of x is equal to the tangent of x minus x, all divided by x squared. For values of x less than or equal to 0, h of x is equal to x cubed times a function m of x, where m is differentiable for all real numbers. Our task is to find the derivative of h with respect to x for all real values of x. All right, let's carefully walk through this problem together. Step 1 is the derivative for x greater than 0. We begin by finding the derivative of the first part of the function. When x is greater than 0, h of x equals the tangent of x minus x, all divided by x squared. Since this is a quotient of two expressions, we apply the quotient rule. Here's what the rule says in words. We take the square of the denominator, which is x to the fourth power. In the numerator, we multiply the denominator, which is x squared, by the derivative of the numerator, which is the derivative of tangent of x minus x. That derivative is secant squared of x minus 1. Then we subtract the numerator, which is tangent of x minus x, times the derivative of the denominator, which is 2 times x. Putting all together, the derivative of h when x is greater than 0 is the following. X squared times the square of the tangent of x, minus 2 times x times the quantity tangent of x minus x, all divided by x to the fourth power. You could simplify this expression further, but this form is already valid for our purposes. Step 2 is the derivative for x less than 0. Now we look at the second part of the function. When x is less than 0, h of x equals x cubed times m of x. This is a product of two expressions, so we use the product rule. The derivative of x cubed is 3 times x squared. Multiply that by m of x. Then add x cubed times the derivative of m of x. So for x less than 0, the derivative of h is 3 times x squared times m of x, plus x cubed times the derivative of m of x. Step 3 is to behavior at x equals 0. Now comes the critical part, analyzing the behavior at the point where the function changes definition, which is at x equals 0. First, we find the right-hand derivative. That is, the limit of the difference quotient as x approaches 0 from the positive side. So we compute the limit of the expression tangent of x minus x, all divided by x squared, as x approaches 0 from the right. To handle this, we use the Taylor expansion of tangent of x around 0. The expansion is tangent of x is approximately x plus 1/3 x cubed, plus higher order terms. So tangent of x minus x is approximately 1/3 x cubed. Dividing that by x squared, we get approximately 1/3 times x. And as x approaches 0, this expression approaches 0. Therefore, the right-hand derivative at x equals 0 is 0. Now for the left-hand derivative, we compute the limit as x approaches 0 from the negative side of h of x minus h of 0, all over x. Since h of x is x cubed times m of x, and h of 0 is 0, we simplify the expression to x squared times m of x. As x approaches 0, x squared goes to 0, and m of x remains finite since it's continuous. So the limit is 0 again. Because both one-sided derivatives at 0 exist and are equal, the derivative of h at 0 exists and is equal to 0. Final answer is, the derivative of h of x is defined as, for x greater than 0, it is x squared times the square of the tangent of x, minus 2 times x times the quantity tangent of x minus x, all divided by x to the fourth power. At x equals 0, the derivative is 0. For x less than 0, the derivative is 3 times x squared times m of x, plus x cubed times the derivative of m of x. This problem is a great example of how to handle piecewise-defined functions. The strategy involves taking derivatives in each region separately, applying the quotient and product rules carefully, using limits to examine smoothness at the boundary point, and applying Taylor expansions near 0 to simplify tough limits. When you're working with a piecewise function that changes at a point like 0, always zoom in on that point. First, check if the function is continuous there. Then compute both the left-hand and right-hand derivatives using limits. And if you're dealing with trigonometric functions, use known Taylor expansions to simplify the expressions. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel and turn on notification bell. Press the like button. Thank you so much.